Hello students, my name is Mahesh Mahale, working as Assistant Professor in Srimati Vimlaben Khilji, Tejukaya Arts, Commerce and Science College, Devdali Camp, Nashik. So in today's lecture, we will discuss the shape of orbital based on Schrodinger equation, which we have discussed in lectures, in offline lectures. So in this lecture, we will see what are types of orbitals and what are shapes of different orbitals. So based on Schrodinger equation, it shows that the shape of orbital are basically in a different shape. For S orbital it is spherical shape, so P orbital it is dumbbell shape, and likewise D and F orbital. We will see the shape of different orbital based on principal quantum number and other quantum numbers. So as we know, the shape of S orbital is basically spherical shape, and the orientation of that orbital is along all directions. Like this is x-axis, this is z-axis, and this is basically a y-axis. So orientation of this orbital is along all the axes. So there is no zero density as that in the origin. So it is basically in spherical shape. So this spherical shape is based on Schrodinger's equation. So in that he has discussed the how that shape is came for the S orbital, and for the S orbital the full form of S is basically a sharp. It indicates the sharp. This is a three-dimensional structure of S orbital. This is this z-axis, this is y-axis, and this is x-axis. So orientation of this orbital is along all the directions. So likewise, if we go from 1s, 2s, 2p, 3s, so the orbitals are oriented in all directions. So as we seen that the orbitals have nodes. So based on the formula for the number of nodes is equal to n minus L minus 1, we have calculated the number of nodes. Like n is for a principal quantum number, L is azimuthal or orbital quantum number, which is based on the shape of orbital, and minus 1. So based on that calculation, we have calculated the number of nodes. Nodes means how many gap is in between that two orbitals. So for example, it is a 2s orbital, so that inner core is basically 1s orbital, and that outermost white core is basically a 2s orbital. So based on that, we have calculated the number of node is equal to n minus L minus 1. So for this, the 2s, so 2 represents the value of n, that is principal quantum number, which is 2. Then L represent the shape of orbital, which is actually a 0. For S orbital it is 0, and then it is minus 1. So 2 minus 1, so 2 minus 0 minus 1 is equal to basically 1. So for 2s orbital, the number of nodes are 1. So that inner gap between that 1s orbital and 2s orbital is basically a node for that orbital. So for 2s orbital there are one node. So based on wave equation, we have discussed for a graph of r upon capital RA versus small RA, which is started from the origin, not from origin, so it is have a one node only. So based on that graph, we have discussed that it has a one node only. For that, the wave, based on that wave function, we have discussed it cuts the x-axis only once through a wave. So that cutting is known as a nodal. So or that plane is not called as nodal plane. So likewise, in case of 3s orbital, so this is basically a 3s orbital in which the inner core represents 1s, the second white core represents 2s, and the outermost blue dark core represents 3s orbital. So based on that, there are number of, so based on this, so number of nodes for 3s orbitals are n minus L minus 1. So n is 3, L is 0, and minus 1. So basically there are two nodes for 3s orbitals which are presence in between 1s and 2s, there is one node, and in between 2s and 3s there is one node. So this is a one node, second node. So this is first node, and this is what the second node is. So based on that formula, number of nodes is equal to n minus L minus 1. We have calculated the number of node for 3s orbitals are 2. Likewise, so Likewise, for p orbital, we know the shape of p orbital is basically a dumbbell shape. So orientation of that dumbbell shape is basically calculated from magnetic quantum number, which is represented by ml. So small ml, small m, and at subscript there is small l. So based on that, we have calculated the values for ml. Values for p orbital are basically px, py, and pz. So values are -1, 0, and 1. These values are calculated from the formula. The value of L is basically ranging from plus L to minus L. So for p orbital, the value of L, that is orbital quantum number or azimuthal quantum number, is 1. So basically the values are starting from plus L to minus L. So for p orbital, the value for L is equal to 1. So values for ml will be +1, 0, and -1. So these value represents the orientation of that orbital. So orientations means this lobe is oriented along which axis. So as we can see here, the orientation of this p orbital is along z axis. So this p orbital is also represented as p x orbital, pz orbital. So likewise, if that lobe is oriented along z axis or x axis, so that lobe or that orbital is called as px orbital. And similarly, so for it is oriented along the y axis, it is called as p orbital. So likewise, we have 3 p orbitals like px, py, and pz based on their orientation along the axis. So if it is on z axis, it is pz, it is on x axis, it is px, and it is along y axis, it is py orbital. So this is what the orientation of that orbital are in the axis or along the axis. So this is the p z orbital, which is directed along the z axis, and the orbitals, lobes of orbitals are likewise. So this is what the dumbbell shape in actual case are. And as we know, there is no electron density in or at the origin, so there has to be a space in between two lobes. So this is what that space indicates, is there is no electron density at the origin. So as in case of S orbital, we have seen it is spherical in shape. The electron density at origin is equals at all the direction. So it is not 0 at the origin, but in case of p orbital, it is 0 at the origin, and it is oriented along those lobes of that orbital, means those axis of that orbital. So it is along the z axis, it is along the x axis, it is along the y axis. So based on that, we have see here there is px or pz orbital, this is py orbital, this is actually a y direction, and this is the x direction. So this is a px orbital. So for the number of nodes for this p orbital, we have know that the p orbital starts from 2p. So that in previous slide we have seen that orbital, it is 2p orbital. So this is the 3p orbital. In that 3p, we need to calculate the number of node for this 3p orbital is, so for p the L value is 1. So as we see, n value for 3p, it is 3, based on the formula for number of nodes for that particular orbital. So n minus L minus 1. So n value is 3, L value is 1, and -1. So it comes 1. So number of nodes for radial nodes for 3p orbitals are 1. So basically this gap in between the 2p and 3p represents the node. So there is one node along each direction or along each axis. So along z axis we have seen this node, along y axis we don't see here node, but there is a presence of node. Along x axis we see a node here. So these are number of nodes present for that orbital. So for this orbital, for 2p 3p orbital, there are one node. So similarly, like for 4p orbital, so 4 minus 1 minus 1, there comes 2. So number of nodes for 4p orbitals are 2. So in between that 2p 3p there is one node, and in between 3p and 4p there is one node. So the gap between that orbitals represents the number of nodes. So there are 3 nodes for, sorry, 2 nodes for 4 p orbitals. So this is the d orbital. So orientation of d orbital, as we know, the shape of d orbital is double dumbbell shape. So this is one dumbbell and this is the second dumbbell. So values for L for d orbital is 2. The values for ml, that is principal or magnetic quantum number, ranges from +2 to -2. So +2, +1, 0, -1 and -2. So there are 5 values for d orbital. So based on that 5 values, the orientation of lobes along the axis or in between the axis are 5. So based on that, the d orbital is subdivided into 5 suborbitals, which is dxy, dyz, dxz, dx square minus y square and dz square. So these are two representations, two representative of that orbitals. So based on that, these two orbitals are in between the plane. So plane is basically y and x. So this is the dxy orbital. Similarly, if those orbitals are in between the z and x, so it is dz orbital, and if they are in between the y and z, so it is dyz orbital. Similarly, this is what the dx square dz square orbital is. So the orientation of this orbital is along the all axis, that is z and x, and the more electrons density is toward the z axis. So this is represented as dz square. Similarly, the dx square minus y square orbital is represented along these orbitals. So they are along the axis. So in a d orbital, 3 suborbitals are in between the axis and 2 suborbitals are along the axis. So these are 5 suborbitals of d orbital, along of which this is the dz square, this is the dyz, this is dxz, this is dyz, dxy, and this is dx square minus y square, which is along the axis. So these 3 orbitals, so 1, 2, 3 orbitals are in between the axis, and these two, so dx square minus y square and dz square, are along the axis. So orientation of that orbitals are along the axis. So number of nodes, to calculate the number of node for d orbitals, are basically, which is starts from 3d. So 3d is one of the orbital, second orbital is 4d. So for 4d, the number of node can be calculated as 4 minus, so d value, so L value for d orbital is 2, so 4 minus 2 minus 1, it becomes 1. So number of radial node for d orbital, so for 4d orbital is 1. So basically based on that, the orbitals are divided. So the space between the orbitals are basically a 1. So radial node is 1 for 4d orbital, which is represented as here. So for in between, this is what the 3d is, this is the lobe of 4d orbital. So in between that gap is called as radial node for that orbital. Similarly for this, there is a space in between 3d and 4d orbital. So this represents the node in that orbital. So likewise, so we can see here for zx orbital, so dxz orbital, the number of nodes are 1. Similarly, so this is the inner orbital represents 3d orbitals, the outer orbital represents the 4d orbital. So the space in between 3d and 4d is basically 1. So radial node for that orbital is 1 in case of 4d orbital. Likewise for 5d orbital, so inner shell is 3d, the second orbital lobe is 4d, and the last outermost orbital is 5d. So in between there are 2 nodes or 2 radial nodes are present, can be calculated by n minus l minus 1. For 5d it is 5 minus 2 minus 1, so it comes 2. So radial node for d orbitals are 2 and can be represented in all the orientations. So for 5 orientations, there has to be a 2 nodes in each lobe. So for 4d there are 1 node, for 5d there are 2 nodes, can be calculated by radial node is equal to n minus l minus 1 formula. At last, this is the 5d orbital, sorry, this is the f orbital, which is triple dumbbell in shape. So 1 2 3 4 5 6. So there are 1 2 and 3 orbitals are oriented in different directions. So there are three different lobes. So this is what the representation of 3D orbital F orbital is. So it is triple dumbbell in shape, and representation of all orbitals are seen here. So based on value of azimuthal quantum number, for F orbital it is 2, F orbital it is 3. So values for ML values, that is the magnetic quantum number, ranges from +3 to -3. So +3, +2, +1, 0, -1, -2 and -3. So there are 7 values. So based on that, there has to be a 7 lobes oriented in all directions. So there is orientation of that F orbital is in 7 directions, in all directions. Like, so there are formation of 7 sub orbitals of F orbital. So they are represented as here. So these are 7 7 suborbitals of F orbital. And similarly, for these we can calculate the values for a radial node is equal to n minus L minus 1. So for F orbital, the value of L, that is azimuthal quantum number, has to be 3. So based on that, we can calculate the values for radial node by the formula n minus L minus 1. So for the F orbital starts from 4f, and the next orbital is 5f. So for this is what the representation of 5f is. So 5f, this is what the representation of 5f is. So based on that, we can calculate the radial node for 5f orbital are 5 minus 3 minus 1, it becomes 1. So radial node in case of 5f orbital is 1. So it is seen here. So the gap between the two lobes are basically a radial node for that orbital. So there is only one gap in between that lobes, the radial which represent the radial node in between that lobes. So for 7f orbital, there has to be a 2 lobes. 6f orbital, there has to be a 2 radial nodes, which can be seen here. So there is 2 gap in between that 3 lobes, which represent the radial node for that F orbital. So in this lecture, we have discussed what are the shape of orbital, what are the different shape of orbital. So for S orbital, it is spherical in shape, and the orientation of that orbital is along all the axes in equal distribution or equal shears. For P orbital, it is dumbbell shape. For D orbital, it is dumbbell shape, and for F orbital, it is triple dumbbell shape. So based on that, based on the formula, radial node is equal to n minus L minus 1. We can calculate the radial node for all different orbitals. So the value for n is basically a principal quantum number, which represents the shell number. The value of L, which is actually a azimuthal quantum number or orbital quantum number. For S orbital, it is 0. For P orbital, it is 1. For D orbital, it is 2, and for F orbital, it is 3. So based on that, we have calculated radial node for different orbitals. So for example, for 3D orbital, if you need to calculate the radial node, so for 3D, so 3 represents the n value, D, the value for D, L value for D is basically a 2. So 3 minus 2 minus 1, it becomes 0. So for 3D orbital, there are no nodes because 3D orbital starts from 3D. So based on that, we have calculated the radial node for different orbitals. So for example, in exam, if you need to calculate a radial node for that particular orbital, which is given in that question, so just apply the formula n minus L minus 1, which is radial node is equal to n minus L minus 1. So we can calculate the different types of different nodes in different orbitals. Thank you.